Well, my dear participants, now I am going to talk about some more examples from gamma distribution. So, here y is equal to r gamma, 1000 observations are being simulated, and shape is equal to 1.5 and rate is equal to 0.0. And then if we want to compute the density on these simulated values, we are giving dfx is equal to d gamma y, and we can run this, and we can represent these density values d fx here, and we can get plots also, but I am not going to plot. See, now p gamma 50, that means probability of the gamma distribution below 50, shape is equal to 1.2 and rate is equal to this thing. This is p gamma. P gamma is 0.54. So, we can verify this result. This we are computing on the basis of exact values. Now, see what you get on the basis of simulated values, and that you can have, that is actually mean of y less than 50. So, this will compute the probability of, this will be the parallel of on the basis of simulated data. It is 0.538 on the basis of simulation. We are getting probability 0.538, whereas exact probability is p gamma 0.5469. So, they are very, that means our simulation is correct. Our simulation is correct. Similarly, if we want mean of gamma, so 61.08 is on the basis of simulated values, whereas exact value is 1.2 divided by 0.02. So, this is the exact value. Exact value is 60, whereas on the basis of simulated it is 61.0. So, they are in close agreement. Similarly, see, now quantile of gamma 0.54, q gamma 0.5469, and shape is equal to 1.2, rate is equal to this thing. So, this quantile should be very close to 50. Yes, it is 49.33. So, because quantile is nothing but inverse image of the CDF. So, the value of the CDF is 0.5469. So, if we want, and probability is 0.5, so quantile will be 49.99, and which is 50, which is equivalent to 50. Compute probability of y greater than 50. It is p gamma. So, this is 0.453069 on the basis of exact values. But from the simulation also we can compute this probability, and that is probability of y greater than 50, and that is 0.462, and on the base, this is on the basis of simulated values, whereas on the basis of exact it is 0.45 and 46. This is the difference. But if we increase the sample size, it will converge better. Say instead of we are having 10,000 observations, then see what will be the mean. It is 0.4525 and exact is 0.453. So this way this improves. If we increase the sample size of simulation, it approaches to the exact value. Now how gamma distribution takes different shape? Because you know there are two parameters in gamma distribution. One is shape, another one is rate. So actually if we want gamma distribution, so we are using curve d gamma, shape is equal to 1.2, rate is equal to 0.02, and from 0 to 200 y lab is equal to density and color is equal to 1. So this will generate a plot. So this is the gamma distribution with shape is equal to 1.2 and rate is equal to 0.02. If we are keeping the rate same 0.02, but our shape is 1, so with shape is equal to 1, it converts to the exponential distribution. So if we will generate this, it will give exponential curve. Similarly, if we are increasing it, here we have decreased 0.2 and we are keeping 1, so it becomes the curve of exponential distribution, whereas here curve d gamma x, shape is equal to, instead of 1.2 it is 1.5. So see what happens, and if curve is equal to 2, see it becomes symmetric, almost it is approaching toward, as the value of shape parameter is increasing, the distribution becomes from skews to symmetric. And lesion top right, lower is equal to shape 1, 1.2, shape is equal to 1, shape is equal to 1.5, shape is equal to 2, and LTY is equal to line type is equal to 1:4, and color is also 1:4. So we need to run the whole chunk to get the output of the graph. See, this is because of the legend command. This solid line shape 1.2, this is this line, and then shape is equal to 1, it is a red line, this one, this is exponential distribution, with shape is equal to 1.5, it is this one which is green, and with shape is equal to 2, it is dashed line. So this line is shape is equal to 2. So as we are increasing the shape parameter, it is approaching towards symmetry, although still it is skewed, but when we will increase this, it may go to symmetry. Now I shall talk about beta distribution. Beta distribution is a continuous distribution in the range of 0 to 1. It is like uniform distribution, but here it can take any shape. Uniform 0, 1 takes only one shape, and that is straight curve. But here horizontal line is being drawn. But here shape is equal to 1 and shape is equal to 2. There are two shape parameters in beta distribution. And if we are simulating 5,000 observations, see what shape it takes. Because shape is equal to 1, shape 1 is equal to 1, shape 2 is equal to 1, it becomes uniform distribution. So when we run this chunk, it creates histogram and then d beta x11. So this is the histogram on the basis of simulated data, and this curve is exact curve. So both are matching, so that means our simulation is correct. It is just like uniform distribution. It is just like uniform distribution, uniform 0, 1. Here shape 1 is equal to 3 and shape 2 is equal to 3. Now we have increased shape from 1 to 3 both. So if these parameters are same like 3 and 3, it will again generate a symmetric distribution. And here see, it is again a symmetric distribution, and we are adding curve d beta x33 add is equal to true. So since this is the exact curve of d beta with shape is equal to 3, shape 1 is equal to 3 and shape 2 is equal to 3, and these are the histograms which are generated on the basis of simulated data. Both are matching, that means our distribution is correct. See, now I am going to simulate shape is equal to 2, shape 1 is equal to 2, but shape 2 is equal to 20. Then see, because here they are not same, so it will generate skewed distribution. It will generate skewed distribution, and here hist y prob is equal to true, y lim is equal to c 0, 0.9. Actually, if we don't keep this y lim, see what happens. See what happens. And we are exactly writing the curve. See here, the upper part gets cut, and here the range is 7. So we have to increase from 0 to 9 so that this should be inside, it should not be cut. And that's why, and that has to be made in the histogram, because this curve is made on the histogram. So y lim is equal to c, minimum limit is 0 and maximum limit is 9. And now we can generate, see, now this is the curve. So here when shape is equal to 20 and shape 1 is equal to 2, shape 2 is equal to 20, it is right skewed. But see what happens if we are changing the situation. If we are changing the situation, say Control Alt I have made y is equal to, here I am going to change. See how I am changing. Control C, and then I am going to paste in this. So here instead of this one 2, we are keeping it 20, and shape 2 we are keeping 2. So here also we have to change 20 and 2 and see what kind of shape we are getting. Here when it was shape 1 was 2 and shape 2 was 20, it is right skewed. And see what happens if shape 1 is equal to 20. See, it is left skewed. It is, if shape 1 gets increases, so it is left skewed, because here shape 1 is equal to 20 and shape 2 is equal to this thing. Whereas if shape is equal to shape 1 is equal to 2, shape 2 is equal to 20, it gets right skewed. And when shape 1 is equal to 3, both are same, we get symmetric shape. And here also, when shape is equal to 1, shape is equal to 2, it is uniform distribution, no doubt, it is also symmetric. It is also symmetric. So this is the effect of changing the shape parameters. Now I am going to talk about inverse CDF method of simulation. T. It is a well-known result in probability that if x follows some CDF f, CDF of x, then fx, here it is not the small x, it is not the value of the x, rather it is a random variable having CDF f, then x follows uniform 0, 1. This implies that one can simulate quantiles from f by using the following algorithm. Here, equal the CDF fx is equal to u and solve it for x, where u is uniform 0, 1. Number second, the equation x is equal to f inverse x will be a quantile from f. So these two things we have to follow. Now we can get simulation from exponential distribution. We can make use of inverse CDF method for simulation from exponential distribution with rate is equal to lambda. Note that. See, I would like to show you these things in the form of PDF because there it is more clear. See, this is the inverse CDF method. Inverse CDF method of simulation. If it is a well-known result of probability that if x follows f, CDF of x follows CDF of x, then fx follows uniform 0, 1. This implies that one can simulate quantiles from f by using the following algorithm. Equal the value of CDF fx is equal to u and solve it for x, value where u follows uniform 0, 1. Deviate. The equation x is equal to f inverse u will be the quantile from f. Simulation from exponential distribution. We can make use of the inverse CDF method for simulation from exponential distribution with rate is equal to lambda. Note that fx is equal to lambda e raised power minus lambda x is the PDF of the exponential distribution. This implies CDF fx is equal to 1 minus e raised power minus lambda x. Thus, what we have to do? We have to follow the algorithm number 1, equal fx is equal to u and solve this equation for x. So, fx is equal to u implies 1 minus e raised power minus lambda x is equal to u, and this implies we take this to the left hand side, 1 minus u is equal to e raised power minus lambda x implies, now take the logarithm of both the sides, log of this side is equal to log of this is equal to minus lambda, and this implies x is equal to minus 1 by lambda log of 1 minus u. Now, how we can generate the R commands? U is equal to R unif 1000, lambda is equal to 0.02 value of the rate, and x is equal to minus 1 by lambda into log of u, simulated quantiles, and then we can check mean of x is equal to 1 by lambda 50, variance of x is equal to this thing, SD of lambda, and then mean of x greater than 50, that is prob, is equal to 0.38, and here we can make a histogram based on simulated data. Then we can exactly plot a curve on this histogram. LWD is equal to this thing, then ebb line V is equal to 50. So I would like, and this will be the output. This will be the output. Here vertical line is at mean 50. So now I would like to close this window and go to these commands. So these are the commands. U is equal to R unif. These are random simulation from uniform distribution. So we can have 1000 uniform deviates, uniform 01 deviates, and then we are assigning a value 0.02 to the lambda. So lambda is 0.02. So that means what? That means mean is equal to 1 by 0.02, and that is nothing but 50. So here then x is equal to minus 1 by lambda into log of this. So these are the simulated results, and these are the simulated results from exponential distribution with rate is equal to 0.02, and these are the simulated results, and we can have a histogram and other things. So what should be the mean of? Mean of this should be around 1 by 0.02, and that is nothing but it should be around 50. See, it is 48.96, around 50. And what should be the variance? It is 1 by lambda square. So it is 1 by lambda square. So that means it should be 1 by lambda square, and lambda is 0.02 whole raised power 2. So this is 2500 and 2306 is the variance. No doubt, if we are increasing the sample size, here instead of 1000, suppose we are having 10,000 random deviates, then we can have x values like this, Control T, and then see what is the exact mean. 1.02, exact mean is 50, and mean of x simulated data should also be 50, 49.66. So it is equivalent to 50. And what should be the variance? Exact variance is 0.02 raised power 2. So exact variance is 2500. And see what is the where of x. It is very close to 2500, 2408.36. So this way we can check our simulation. See, mean SD. Now mean of x greater than 5. So that is nothing but probability of x greater than 5, because if we talk of x greater than 50, the mean greater than 50, the value of x greater than the mean is 50. So these are the values which are being simulated. If true, it is assigned 1. If false, it is assigned 0. So if we will take mean of these, it is nothing but probability of, if we want probability of x greater than 50, so this is nothing but mean of x greater than 50. So it is 0.36. It is 0.36. Mean of x greater than 50 is 0.36. So this way we can, and we can verify it from P exp, here it is 50 and rate is equal to 0.02, and because it is greater than, so lower dot tail is equal to false. So this is the exact value, 0.3678 is the exact value, and on the basis of simulation 0.3678. So both are same, both are matching. So that means our simulation, the simulation method we have implemented is correct, and that is based on the inverse CDF method. Now here we are going to make a histogram on simulated data, and then we are going to add a curve DEXP, rate is equal to 0.02, add is equal to true, LWD is equal to 2, and we are going to add a line at V is equal to 50, vertical line at 50, color is equal to red, and LWD is equal to 2. So when we run this command, this is the output. This is because of LWD is equal to 2. So this is the exact exponential distribution curve, and this histogram is made on simulated data which we have simulated on the basis of inverse CDF method, and this vertical line is at mean, and that is 50. So these things. Now we can talk about Weibull distribution and then certain exercises, then chi-square distribution, some exercises, then quantile plots. So these things I shall discuss tomorrow in my lecture about how we can simulate data from Weibull distribution, and how we can make histogram, and how we can verify these results. So this is all for today's.